In this video, we will conclude our series on the method of images problem, which says that we have an infinite plane that is conducting and grounded, and we have our x, y, z axis like so, z, x, and y, and we set it up that we had a positive charge q, a distance d, above this infinite conducting plane. So in the previous videos, we have found that on this plane, the total induced surface charge was negative q, and the charge distribution was negative q d over 2 pi 1 over x squared plus y squared plus d squared to the power of 3/2. Now in this video, what we want to do is we want to find out what is the force that this charge, positive q, experiences due to the electric field produced by this infinite conducting plane, and what is the energy associated with it as well. We can right away determine that the force felt by this charge, positive q, will be an attractive force because the total induced surface charge will be negative q. If we recall from the first video in this series, the potential in this vicinity z greater than 0 is q over 4 pi epsilon naught, and then in brackets we have a long equation, which I will just write out quickly, 1 over minus 1 over x squared plus y squared plus z plus d squared. This is what we found in the first video of this series. And what we said was that this potential for this setup was the same as the potential produced by a different setup, which had a positive charge q, a distance d above the plane, and a negative charge, negative q, a distance negative d below the plane. So what we said was that this potential is the same for both, and therefore we can also extrapolate to say that the electric field will be the same for both distributions in this vicinity z is greater than 0. And now the electric field produced by the other charge distribution, where we have a positive and a negative charge, will be 1 over 4 pi epsilon naught, and we're looking at the field produced by this negative charge, negative q, and it will be at a distance 2d squared and directed in the z hat direction. So what that means is that the electric field in this region here, close to the positive q in this setup with the infinite conducting plane, will be the same as from the charge distribution where we had a positive and a negative charge produced by the electric field of the negative charge. Therefore, we know that the force is just equal to q, the charge positive q, times this electric field, and we can say that the force felt by this positive charge q is negative 1 over 4 pi epsilon naught q squared, where we have this q from above and this q from below, over 2d squared, directed in the z hat direction. And so our final force, F, that is felt by that positive charge q, a distance d above the infinite conducting plane, is simply minus 1 over 4 pi epsilon naught q squared over 4d squared in the z hat direction. And of course, this is an attractive force that the positive charge will feel because the total induced surface charge is negative q, and this positive charge q will be pulled towards this infinite conducting plane with this force. So what we just found was that the force that the charge positive q experiences due to the infinite conducting plane is F is equal to minus 1 over 4 pi epsilon naught q squared over 4d squared in the z hat direction. And of course, it's a negative force because it's the force of attraction between the charge and the plane. We want to conclude this video by determining what is the energy associated with this charge distribution. And we can do that by determining what is the work that needs to be put in order to bring a charge positive q from infinity to a distance d above the infinite conducting plane. And this is done by integrating a force dotted with an infinitesimal line element dl. Now this force is not the same force that we have over here, because this force is the force of attraction felt as that positive charge falls from infinity to this distance d above the infinite conducting plane. This force is the force that we want to exert on the charge in order to prevent it from falling any further. Of course, this means it has to be equal and opposite as we carry this charge in from infinity and place it at distance d above the conducting plane. What that means is that our force will become positive 1 over 4 pi epsilon naught q squared over 4z squared, where now we use the variable z because we're traveling from infinity to d in the z direction, and we're not simply fixed at position D, and this is in the z hat direction. And we're going to dot that with the infinitesimal line element dl, which is just dz times z hat, if we're working only in the z direction. So we can do this dot product, which says that z hat dot with z hat is just 1. And we end up with the integral of 1 over 4 pi epsilon naught q squared over 4 z squared times dz. We can pull the constants outside of the integral, and we have 1 over 4 pi epsilon naught q squared over 4, the integral of 1 over z squared dz. Now the limits of this integral will be from infinity, positive infinity, to d, where we start at distance infinity, positive infinity, away from the infinite conducting plane, and we move that charge to distance d above the infinite conducting plane. By solving this integral, we have w is 1 over 4 pi epsilon naught q squared over 4, negative 1 over z, integrated from positive infinity to d. And we can solve this and say that negative 1 over 4 pi epsilon naught, we pull the negative out, q squared over 4, and we have 1 over d minus 1 over positive infinity. Of course, 1 over positive infinity is just 0, so that will cancel, and we end up with the work required to carry our charge positive q from infinity to a distance d above the infinite conducting plane is simply minus 1 over 4 pi epsilon naught q squared over 4d. And this is the energy associated with our charge distribution and concludes our method of images problem.